Good morning. Hello, everyone. I'm glad that all of you are here for today's presentation of my PhD defense under the title Dynamic Compression and Liquid Transport in Fiber Systems under Press-Nip Conditions. But before starting and showing you the results of my thesis, I want to introduce you to one particular situation that maybe all of you have seen in different manners around the whole globe. And this shows the deposition of a huge amount of fossil-based plastic waste, which is dumped into the environment. And as fossil-based plastic waste will not disintegrate for years, centuries, or even decades, or even centuries, this creates a long-term pollution problem for our whole society. However, the problem is not new. So many solutions for this problem already had been proposed. And among those, there is this one idea to increase the usage of fiber-based packaging solutions, which are biodegradable solutions, such as paper cups, paper trays, and paper plates. However, in order to upscale the full potential of this solution, one needs to ensure that the process of paper making or of making the base material, which is paper, can be conducted in an ecological and economical feasible way. And within an industrial scope, this is done in a so-called paper machine. So the paper machine that you can see on this picture is a huge and enormous machine that looks rather complicated. However, the process of paper making is rather straightforward. So what is happening in paper making is that you basically have a suspension of cellulose fibers and water that you apply using a head box on a so-called wire, where the initial sheet is formed. Afterwards, you transport this wire through a so-called forming section, where vacuum dewatering is used to further increase the solids content of the wet sheet. Afterwards, the wet sheet is transported into a so-called press section, where the mechanical dewatering of the wet paper web is taking place. All the remaining water in the wet paper web that cannot be removed by wet pressing is then evaporated in a subsequent dryer section using steam-heated cylinders before the dry paper web is wound up on a reel. If you study this process now in more detail, you will figure out that all water we cannot remove by wet pressing needs to be evaporated in the dryer section. And as the evaporation of water is an energy-demanding process, basically the efficiency of the whole paper-making process is determined by the efficiency of the wet pressing process. So let's have a closer look at wet pressing. So within a state-of-the-art paper machine, the wet pressing is conducted in a so-called shoe press nip. And the way a shoe press nip works is basically that you have the wet paper sheet, which is basically entering the shoe press, laying on a so-called press felt. And in the shoe press, the nip is basically formed by a flexible shoe press belt, which is pressed against a counter roll. In the shoe press nip, an hydraulically loaded shoe creates a deformation of the paper web, press felt, and the press belt. And this happens basically as a very fast process, a highly dynamic process. However, besides creating a deformation of these substrates, also an hydraulic pressure gradient is being created, causing a flow of water from the top surface of the paper web through the press felt into the deforming voids of the press belt. As mentioned, the overall efficiency of the wet pressing process basically determines the efficiency of the paper making process. Consequently, many researchers before me have focused on investigating different aspects in wet pressing. Among those, many focused on the dynamic deformation behavior of the wet paper web, like Hannes Vomhoff, but also deformation of the press felt was a study. Anyway, observations from industrial paper machines indicate that also the specific combination of the press felt and roll cover will have an influence on the overall dewatering process performance. Furthermore, also nip saturation, which is the result of the deformation of the network in the nip, but also the water load of the nip, will have an important influence on the dewatering process performance. Consequently, this thesis aims to increase the understanding in the compression and liquid transport within these fabrics press felt and press belt under press nip conditions in order to further increase the dewatering process performance. But before basically conducting studies, it is now important to get a basic understanding in the principal fabric structures, press belt and press felt. So let's have a closer look on those. So starting with the press belt, which I have with me here, the press belt as such is a polyurethane composite created by a polyamide 6 matrix, fiber structure which is casted in a polyurethane matrix. On the top surface, you have grooves that are used for venting the nip. So these grooves create a so-called void volume, which allows water coming from the press felt to flow into the grooves of the press belt and leave the nib in machine direction. It is important that the void volume of these grooves matches the water load in the nib to create saturated but not oversaturated conditions. Furthermore, we have the press felt. And the press felt, which you can see here, it's basically a fiber network which is created from a woven polyamide 6 base fiber layer. And on this woven base fiber layer, you have non-woven bed fiber layer, also created consisting from polyamide 6 fibers. And these bed fiber layers on the top and on the bottom are attached to the base layer using a so-called punch needle process, where barbed needles create one mechanically entangled network. This press felt, which is the result of the punch needling process, offers a certain void volume that is necessary to allow water coming from the paper web flowing through the press felt into the voids of the roll cover or press belt. So now you're familiar with both press felt and press belt. And now I want to show you how we organized this study. So as mentioned, the press nib is a highly dynamic event, and the voids of the press belt needs to fit the water load in the press nib. So therefore, we started with investigating the press belt deformation behavior, which was basically the result, or the results were documented in paper 1. Afterwards, we continued in calculating the loss of the void volume that was documented in paper 2. But besides studies of the press belt, we also focused on the interface between press belt and press felt, which was a topic in the paper number 3, where we studied macroscale stress variations that are created by interfacial effects. Finally, we shed some light on the press felt and studied the static liquid distribution in the press felt, the dynamic or the capillary liquid spread in the press felt as function of the saturation, but also the effect of flow instabilities that occur during the imbibition of dry porous networks. And all of these studies were documented in papers 4 to 6. So basically, as you can see, we conducted studies around the whole press nib in order to increase the understanding in the fabric deformation and liquid transport behavior. So after that, let's start with the first study. And that was the study on the dynamic compression characteristics of the press belt. And the principal research question in this specific topic was, as you can see on this nib picture, to study the deformation of these grooves. And in order to do that, we basically created a mechanical testing setup that allows to create nib-like boundary conditions in a laboratory environment. So with these nib-like boundary conditions, we could simulate basically the dynamic stress-strain behavior of the press belt and recorded dynamic stress-strain curves. With these dynamic stress-strain curves, we then created, or we then used these stress-strain curves in a viscoelastic model that simulate the press belt deformation behavior. And we solved this viscoelastic model for the strain in the grooved section, which basically is equivalent to the void volume loss. As a result, you can see the void volume loss as a function of both the external load, but also the load rate. And the load rate in the scope of this thesis is a metric for the dynamics that is applied in the shoe press nib. So low load rates basically are more or less a quasi-static impulse, and a high load rate is basically a sharp bump, a very, very dynamic impulse. Afterwards, we did verification of the whole method using high-speed camera. But let's have a closer look on the results. And as you see, this is basically like a 3D chart depicting the void volume loss on the z-axis as a function of the load on the x-axis and the load rate on the y-axis. And what you can now nicely see is the void volume loss, which is basically the deformation of these grooves, of course, increases with increasing load. But it also decreases with increasing load rate, meaning that the viscoelastic effects of this matrix decrease the volume loss. And for a practical paper maker, that would mean that if you increase the paper machine speed, you would lose less void volume. So you could use different belts. So this basically allows us now to customize this groove pattern regarding specific operation conditions of specific paper machines to always reach saturated and perfectly fitting conditions. Furthermore, you can also see that the polyurethane matrix formulation has a prominent influence on the evaluation of these void volume losses. So also the polyurethane that you use for these press belts has an important influence on the overall behavior. Besides that, I want to shed light on the interface between press belt and press felt. Because in the paper machine press nib, the press felt is basically compressed against the press belt. And looking at our press nib again, our area of investigation now shifts from the press belt towards the interface area. And the reason, or the research question behind this was if macroscale stress variations induced by the groove pattern of the press belt would influence the press felt dewatering. And the reason why we came to this research question was the following hypothesis. So as you see, the press felt can only be compressed on the land areas of the press belt, meaning that you will create a two-dimensional compression state in the press felt. And as the local compression of a porous media determines its local porosity, and that again determines the local permeability, you will end up impeding a 2D permeability field in the press felt that is specific regarding the specific used, basically groove and land profile. So we wanted to investigate this, the dewatering and the effects on the dewatering of this a bit more in detail. So we proposed the following dynamic testing setup, and I have a 3D printed model with me now. So this is basically the model of that. And what it does is that we have a sample of the press felt here that we place in a carrier between the impact body and the target body. We saturate the press felt with water and then apply a dynamic impulse at a certain load rate against the groove pattern that is on the bottom. Using eddy current sensors allows us to calculate the stress and the strain, but also we can calculate the dewatering that we apply or that we reach during this impulse. So on the bottom, as mentioned, we have this groove pattern. And in the experiment, we used 3 different groove patterns, pattern A, B, and C. While pattern A is a quite homogeneous and even groove pattern, pattern B is a more coarse groove pattern, and pattern C is a very coarse groove pattern. And doing now dewatering tests at different load rate gives you results that look like that. So what you see is on the x-axis the load rate, so the dynamic metric, on the y-axis the dewatering. And what is now apparent that especially for high load rates, which are the industrial relevant load rates, you see that the groove pattern B shows the highest values for dewatering. And this is somehow interesting because pattern B impedes macroscale stress variation at an intermediate level. On the other side, pattern A, which is quite homogeneous, and pattern C, which is inhomogeneous, both create lower values of dewatering. So with that, we came to the point that stress variations induced in the press felt can somehow stimulate dewatering. Using this data now, we basically conducted an optimization algorithm where we could predict one groove pattern that is able to further increase the dewatering of by around 7%. So that basically allows us to have a custom optimization algorithm to predict the perfectly fitting groove pattern for a specific press felt, meaning that we can now tailor the combination of press felt and press belt, which is a novel insight and gives a high value for basically all press nib. And yeah. So that was a success. And besides these stress variations in the press felt, we were also interested in the liquid transport through the press felt. And that was a matter of study in papers 4 to 6. So at first, we basically were interested in the partly saturated state, because previously we were investigating the saturated state. Now we're looking at the partly saturated state. And as the press felt is a porous media, water can be basically stuck everywhere. So we wanted to study where the water in the press felt is in the partly saturated state. And that was done using a tomographic approach. So what we did was we created this compression cell where we placed a sample of the press felt in this PMMA tubing, applied a few droplets of liquid on the top, and then applied a static load. After applying the static load, we conducted the tomographic scan and the reconstruction. And if you do that, you will end up with results that look like this. So what you see is basically a grayscale picture. You see fibers, you see air, you predict that there is water, but you cannot distinguish between the individual phases. And this is why the reason is that we have more or less identical X-ray attenuation coefficient between water and polyamide 6 fibers. And to overcome this issue, we found a nice way of staining the water with potassium iodine, which increases the X-ray attenuation coefficient and therefore allows us to distinguish between fibers, the liquid, and the water, so the multi-phase system in a 3D spatial domain. So using this method, we could then investigate the phase distribution in the press felt at partly saturated states at different load situations. So let's have a look on the results. And even though we have the full 3D spatial information, I want to focus this result presentation now on the 2D case. So by basically projecting the liquid densities on the in-plane and out-of-plane surface. So if you look to the basically to the unloaded case at 0.1 megapascal, for the out-of-plane direction, so for this plane, you see that the liquid is more or less bound in the top bed fiber layer. And this is because you basically have fine pores in the top bed fiber layer, creating high capillary pressure, which keep all the liquid there. On the other hand, if you look to the press field in the in-plane direction, you see that the liquid is more or less randomly spread along the press field. If you then increase the compression to 3, 8, or 12 megapascal, you see for the out-of-plane, the liquid is redistributing in the thickness direction to the backside bed fiber layer. However, for the in-plane, you see that there is no real redistribution of liquid going on. So why is this the case? And in order to give answer to that, let's have a look on the unloaded case. So as already mentioned, the bed fiber layer creates fine pores because we have fine fibers creating high capillary pressure that keep the liquid on the top. But if you look a bit more close to this image, you see that also traces of liquid going downwards are visible. And actually in this layer, we have the coarse base fiber layer, which has coarse and big pores creating only low capillary pressure. However, due to the punch needling process that is applied in the manufacturing of the press field, you create fiber pillars that create local areas of fine pores in the coarse bed fiber layer, creating high capillary pressure that basically allow the water to flow through these fiber pillars into the backside bed fiber layer. So this sheds some light on the punch needling process, which is not anymore only seen as a manufacturing process, but also a process that modifies the liquid distribution within the press field. And that was a novel insight. So now we studied basically the static liquid distribution in the press field. Anyway, we also had this observation from paper makers that the press nib is basically showing higher nib dewatering if you increase the saturation. So we wanted to study this process in another way. And doing basically such a study, we proposed using a time-resolved X-ray radiography study. And the way it works is basically that we had a piece of press field and applied droplets of water, subsequent droplets of water on this piece of press field. At the same time, we applied an X-ray beam and directed this X-ray beam through the uppermost bed fiber layer and recorded the whole process on an X-ray detector system. So doing that gives you results that look like this. So what you see here is basically a grayscale image of the top bed fiber layer when the press field is still dry. The first droplet is then released from the top, is arriving at the press field and at some point bursting. And after the burst, it is redistributing in the press field base layer. So you see it is redistributing here. If you apply more and more droplets, you will end up increasing the saturation until you, for example, arrive at droplet 7, where you already have around 27% of saturation. You again release the droplet. It will go down, reach the press field, at some point burst, and after the burst, redistribute in the base of the press field. If you see, the process of redistribution is way faster here than here. So that already gave us an idea that there is a difference that is basically dependent on the saturation. So we wanted to bring numbers behind this difference. And that's why we came up with a Lucas Washburn-based model that basically calculates the liquid content in the uppermost bed fiber layer. And with that model basically was then used to fit to the experimental data we obtained at the synchrotron beamline, calculating a so-called transport index in Z direction, which is a metric for the capillary liquid transport speed in the thickness direction. And plotting this transport index in thickness direction as a function of network saturation reveals that the liquid transport is basically exponentially increasing with increasing network saturation. And that was a novel insight that, first of all, coincides with results for relative permeability measurements of fiber networks in the plane direction, but on the other hand, kind of explains why saturated or press nibs with higher saturation show higher liquid transport speed and also higher dewatering. So that could more or less prove a theory we have in dewatering that comes from the paper machine side. Besides this more macroscopic investigation, we were also interested in the microscopic basically process of liquid imbibition in porous media. Because previously we studied basically you've seen the picture of the droplet arriving at the press belt on the macro scale, but we wanted to see the flow instabilities that occur during the filling of porous networks in 4D. And doing 4D tomography, meaning 3D plus time, is a quite challenging task because doing tomography requires sample rotation. And if you want to have a high temporal resolution, you might end up doing very fast sample rotations. And fast sample rotations will impede high centrifugal forces, which sets limits in studying flow mechanisms. And one way to overcome this is using the so-called XMPI technology. XMPI is X-ray multi-projection imaging, which is available at the 4MAX beamline at the Max Voss synchrotron in Lund. So what we basically did, or how actually XMPI is working, is that we have an initial X-ray beam that is split using several crystals into several sub-beamlets. These sub-beamlets then penetrate or have one intersecting point, and at this intersecting point of the sub-beamlets, we place our sample, which I brought here with me. The sample, you cannot see it. It is inside this PMMA tubing. You see this PMMA tubing, and inside we have this sample. It's basically an artificial porous media we created using a nanoscribe 3D printer. It consists out of perfectly spherical pores, which are interconnected by throats. Then we applied some liquid from the top and gradually investigated the filling process of these pores. And by using X-ray cameras that record every single X-ray beamlet, we then got several projections. And using these individual projections from the individual cameras and using advanced reconstruction algorithms, we can then reconstruct the 3D spatial domain for each frame, so get the 4D, basically the 4D tomography. So doing the experiment, you will end up with the following results for the individual cameras. So you see liquid is penetrating the network from the top, filling individual pores at individual times. And you see the whole process basically from different angular directions. So this is the result of the XMPI. Feeding all this data then into the advanced reconstruction algorithm reveals results that can look like this. So here on this picture, you can see the 3D domain and different pores in different colors, indicating basically the time when they fill. And you see that not all pores fill at the same time. So one pore fills after each other, and you see that the filling process doesn't start in the middle, it starts on the side, and it's a diagonal sidewise process. You can also plot the pore filling factor as a function of time, basically also highlighting similar effects, but you can see that the pore filling as such, it's not a continuous process, it's more a jump process, so a very fast process, which is a so-called Haines jump, which is frequently reported in literature during filling or drainage of porous media. Having these data, we can then also calculate viscous and capillary pressure losses during this jump process and see that the Haines jump as such is dominated by capillary pressure loss, which aligns with results in literature. So doing this experiment basically shows the capabilities of XMPI studying drainage and filling processes in porous media. And for the first time ever, we could show these processes using low viscosity fluids on a sub-second scale. But with that, I want to come to a summary and show you what we reached in the scope of this thesis in order to increase the understanding in the press net behavior. So we started with the press belt and came up with this calculation model to predict the correct void volume. And that is now a very important model for paper makers in order to choose the correct press belt, because with that we can optimize the press belt to our operation condition of the press section in order to achieve fully saturated conditions and optimize dewatering under our specific operation conditions. Furthermore, we showed that the interface really matters for paper making. So with that study of the microscale stress variations, we could show a method how to tailor make the groove pattern for a specific press belt in order to obtain the highest possible dewatering. Finally, we shed some light on the press felt, first of all, highlighting the importance of the punch needling process, because punch needling is not only a manufacturing process, but also a process that modifies the liquid distribution in the press felt. Before we demonstrated that also the saturation state of the press felt is of high importance in paper making because it modifies the capillary liquid transport. So to sum everything up, we achieved an increased understanding, or we created an increased understanding in the fabric behavior under dynamic nib conditions, which allows for customizing the press nib regarding specific operation conditions that further basically increase the dewatering process performance, which can increase the economical and ecological efficiency of the whole paper making process, leveraging paper to be produced in a more efficient and cheap way. Finally, we also identified the punch needling process as an important process that modifies the liquid basically transport properties in porous media. Besides that, I want to give a quick outlook and highlight one particular thing. So I always showed this nib image, but I never really explained these green arrows that go backwards from the press felt into the paper web. And this process is called rewetting, and it happens in every press nib. And even though it is frequently reported, there are no really effective countermeasures there so far. However, using the XMPI technology would now allow to study this rewetting process in 4D, which would be the first time ever visualization of rewetting and would allow to study effective countermeasures for rewetting, which would further increase the paper machine pressing process performance. But with that, I want to close my presentation. I want to thank my supervisors, Daniel Söderberg and Thomas Rosen, for the scientific guidance in the past years. And I also want to thank Voith Paper for founding this work. Thank you.